so that you can refer back to it. And I will also post the notes on a Blackboard, and I will connect my other device right now so that we can do notes with that. Okay, format of the final, excuse me. It's going to be just like the format of the midterms. 4 long questions, 4 short questions. I'm giving you all day because I know you have other things going on that day, but I don't intend for it to take longer than the midterms took. In terms of what's important from each, you can assume that there'll be 1 question, 1 long question, 1 short question from each midterm, and 1 long question and 1 short question about what came after the midterms. In terms of what's important on the first midterm, Taylor series, very important because the whole theme of this class is taking functions and breaking them into pieces. On the second midterm, definitely eigenvalues and eigenvectors of matrices, and vector calculus could also be important since you're going to need to use that in E&M either next semester or next year. On the third midterm, anything with Fourier series or Fourier transforms, since those get used everywhere. And after the third midterm, Legendre polynomials will be more important than Bessel functions because Legendre polynomials show up in more contexts. Bessel functions get used a lot, but Legendre polynomials get used even more. Likewise, spherical harmonics. So what do you want me to go over?
I had a question about this most recent homework.
Sure. Which question?
The last one. When you're determining the orthogonality relationship, how do you show what the bounds are for the integral?
Okay, so the orthogonality relationship, this is something that came up earlier. It comes down to you need something to be 0 at the boundaries. So the integral from a to b of yj star, and then you have this Sturm-Liouville operator. You can do integration by parts, and you get p of x, which shows up in the differential equation, times yj star times the derivative of yi minus this symmetric term. We've got the derivatives of yi and yj, and this should be, yeah, that's a p of x. So this term here is symmetric. This one isn't. The non-symmetric term has to go away, which means that p and or y and or the derivative of y has to be 0 at the bounds. And it really comes down to the form of the equation and the nature of the situation you're describing. Sometimes p is 1 minus x squared, like in the Legendre equation, or the square root of 1 minus x squared in some equations that we didn't study here but do show up. In that case, if p is 0 at both of the bounds, then it automatically works. Sometimes p is 0 at one of the bounds and y is 0 at the other. Sometimes y is 0 at both of the bounds because maybe you're doing a particle in a box, or you're doing a function that has to be normalized, like a wave function whose integral has to be 1, which means the wave function has to go to 0 at plus or minus infinity. So it comes down to the nature of the problem, but one way or another, you need to pick bounds such that either p of x from your Sturm-Liouville operator and or y and or dy dx will be 0 at the bounds.
And you can pick any of them that you want, really?
Yeah, if it obeys the Sturm-Liouville equation, if it obeys an equation that involves a Hermitian operator, then as long as you do the integral in such a way that this term goes to 0. See, here's where it comes from. It comes from the fact that, let's just start with this fact. D by dx, p of x, dy dx equals lambda rho of x, y. And I know that rho and p look similar, but wasn't my idea to pick those symbols. Anyway, if I have yi lambda I yi, I can multiply by y, that should be a j, yj star and then I can integrate from a to b dx. And on this side, I can use integration by parts. I call this u, I call this dv. And so I wind up getting yj star p of x dyi dx evaluated at a and b minus integral from a to b of p of x dyj star dx dyi dx Now here's the thing, I could swap I and j. If I swap I and j, this is symmetric. This is symmetric. This is 0. But that changes, all right? That goes from I to lambda j. It becomes lambda j if we swap our labels. Whereas this thing is symmetric up to that complex conjugate that we're not going to worry about. And this is symmetric. So I'm getting the same integral. I'm getting this integral either way equals this integral either way multiplied by a different constant. The only way that one integral can equal two different things multiplied by two different constants. The only way that this integral can be equal to two different constants times that integral is if they're both 0. If I've got it at integral 1 equals lambda I times integral 2 and lambda j times integral, that should be 2. Well, lambda I times integral 2 equals lambda j times integral 2 if integral 2 is 0 and then integral 1 is 0 as well. That's the only way that all of this can work. Does that make sense?
Yeah.
So there are, although we haven't dealt with it, there are functions that are orthogonal on more than one domain. They're orthogonal on more than one domain because it turns out that due to the nature of the problem, p and or y and or the derivative of y are 0 at several points. And because they're 0 at several points, you can pick more than one set of endpoints and still get orthogonality. I haven't studied them too much, but it's on my list of things to learn. The prolate spheroidal wave functions obey two very different types of orthogonality relations. And so they wind up getting used to construct interesting ways around the diffraction limit. Okay, then there was a question in the chat, problem set 13, number 1. I can go over that. me switch to that problem. Okay, so problem set 13, number 1. F of theta equals the sum of CL, PL, cosine theta. That should be from L equals 0 to infinity, excuse me. We know that that's also cosine to the 4th theta. And so I asked you for the first several coefficients. Well, first of all, this is an even function, which means it can only contain even Legendre polynomials. It won't have any of the odd Legendre polynomials. So I can immediately conclude that C1 equals C3 equals C5 equals 0. Then for the other ones, I just say, okay, the integral, I multiply everything by CL prime. So I take the integral from theta equals 0 to pi, f of theta, PL prime, cosine theta, sine theta, d theta. That is going to be the sum from L equals 0 to infinity of the integral of PL, PL prime, sine theta, d theta, CL. Okay. And so CL, if I do this correctly, this integral here is 0 unless L prime equals L. So then I get that CL integral of PL squared of cosine theta, sine theta, d theta, 0 to pi, that is equal to the integral of cosine to the 4th theta, sine theta, PL of cosine theta, d theta. So then CL is this integral up here, cosine to the 4th theta, sine theta, PL of cosine theta, d theta, over the integral from 0 to pi of PL squared of cosine theta, sine theta, d theta. Does that answer your question? Just realized I needed to let me write a note to myself about something with some grading. There was a mistake on problem set 14, problem 3. I wrote e to the I omega t when I should have written e to the minus I omega t, and that explains the -1 in a whole bunch of answers. So this afternoon, I'm going to be going back and giving people a bunch of points back on problem 3. Let me just write that into my calendar or I will forget it. Other questions? Anyone? The Taylor expansion from midterm 1 without expanding. Well, all Taylor expansions are expansions. I think what you're asking is there a way to do that Taylor series without taking all of the derivatives? Most of the time when we use a Taylor series in physics, we can write it in terms of one of these Taylor series, e to the x, ln of 1 plus x, sine x, cosine x, or 1 plus x to the n. If you know those Taylor series, that gets you a very, very, very long way. And so in the midterm, we had, this is something we went over with the first group, so I'll go back to those notes. In the midterm, we had a problem like this. We had v is some constants times 1 over this square root minus 1 over that square root. We can start by, we were told to assume that d is this tiny variable. So d is the thing that we're going to be expanding. And we will go over question 3 on midterm 3 after I'm done with this. All right, so d is the tiny thing, the thing that we're expanding in terms of. There were 2 ways to do it. One is to take derivatives. But if we take the derivatives, we will, assuming that we take all of those many, many derivatives exactly correctly, we will get the right answer. It's also like reinventing the wheel. Now, there's a lot of room in this world for people who reinvent the wheel. If you reinvent the wheel and give it some name other than a wheel, if instead of calling it a wheel, you call it circular transportation, then you can give workshops and make a bunch of money off of people who are too stupid to realize that this hip, new, trendy thing, which sounds so amazing, is in fact something that is very, very, very old. But for this problem, it'd be better to recognize that we've got something big plus something tiny. So the first thing we do is write it all out. We can't completely get rid of d. If we completely get rid of d, then there's really nothing to say because we wind up with something that doesn't depend on d. But because d is much less than z, we can keep z times d and get rid of d squared over 4. So d squared over 4 goes away. Then we factor out r squared plus z squared. We factor out the big thing. We're left with r squared plus z squared times 1 plus zd over z squared plus r squared. And then the other denominator, r squared plus z squared times 1 minus zd over r squared plus z squared. And now what we've got is we've got 1 plus or minus a tiny quantity. Here's our tiny quantity, raised to the power 1/2, or actually negative 1/2, because 1 over the square root is the power negative 1/2. So we can write all of this as 1 plus zd over r squared plus z squared to the negative 1/2 minus 1 minus zd over r squared plus z squared to the negative 1/2. Then we just use the fact that 1 plus x to the n is roughly 1 plus nx. And so 1 plus zd over r squared plus z squared becomes 1 minus 1/2 zd over r squared plus z squared. And then we subtract off, I feel like there's something wrong here. Oh no, there were 3 minus signs. You get a minus sign from the fact that we're subtracting in the first place. Minus sign from the fact that instead of zd, we have minus zd. And a minus sign from the power negative 1/2. We multiply those 3 minus signs by each other and we get a minus sign. So you get 1 minus 1/2. The 1/2 comes from the exponent. 1 minus 1/2 ZD over R squared plus Z squared. Then you subtract off the 1 from here. Then we subtract another 1/2 ZD over R squared plus Z squared. And minus 1/2 is just minus 1. And so we get the Q from our original constants up top. We get the ZD up top from here. And then we have R squared plus Z squared to a couple of different powers. You've got the square root of R squared plus Z squared that we factored out at the beginning. And we've got ZD over R squared plus Z squared. So we've got R squared plus Z squared to the minus 1/2 multiplied by R squared plus Z squared to the minus 1. And so that winds up being R squared plus Z squared to the minus 3/2. And so we have 1 over R squared plus Z squared to the 3/2 in the denominator there. Any questions? Jason, did that answer your question satisfactorily, or is there more you want to follow up on there? All right, then there was a question in the chat, question 3 on midterm 3. So let me go to midterm 3. All right, the convolution. So we're supposed to compute the convolution of a top hat function with a Lorentzian All right, well, the convolution, so we've got L star pi. That's going to be the integral of L of x minus x prime times pi of x prime dx prime. But pi is only non-zero between plus and minus a over 2. So this must be equal to the integral from minus a over 2 to plus a over 2 of 1 over 1 plus x minus x prime squared over w squared. Dx prime, right? And that winds up giving us, let's see, if I divide by w and multiply by w, and I make the u substitution, u equals x minus x prime, and then d x minus x prime over w So x prime is equal to, let's see here, UW is equal to x minus x prime. So x prime is x minus UW. So dx prime is minus W du. So then when x prime, let's see here, u would be x, or lower bounds. U is x minus x prime over W is equal to x minus plus or minus a over 2 whole thing over W. So we're either going to get x minus a over 2 over W or x plus a over 2 over W. So we put all this together, L star top hat equals the integral from x equals, now we have to be very careful here because the way this was defined won't be an integral from x equals, it'll be an integral from u equals x plus a over 2 whole thing divided by W to u equals x minus a over 2 whole thing divided by W. You may be saying, but isn't this the larger one? Yeah, it is the larger one. But we didn't say integrate from u is small, from a small value of u to a big value of u. We said integrate from x prime equals minus a over 2 to x prime equals plus a over 2. And when x prime is minus a over 2, where you got x minus a negative number, which is x plus something. And when x is positive, well, sorry, when x prime is positive, we've got x minus positive number, which is going to be a smaller thing. So this is correct. And then dx prime is minus W du. So we've got a minus sign here. We've got these limits of integration. We can flip our limits of integration and get rid of the minus sign. So we get the integral from u equals x minus a over 2 divided by W to u equals x plus a over 2 divided by W. There's a W here, du over 1 plus u squared. All right. That was a long slog, but the integral of 1 over 1 plus u squared is arctan. We're almost done. We've got W arctan of x minus a over 2 divided by W, x plus a over 2 divided by W. And from there, it's just plug in. Stephen, does that answer your question? Okay, what else can I go over? Midterm 3, question 1b. Sure. Find that. Okay, midterm 3, question 1b. We're given a function that's only non-zero in a finite range, and it's 0 everywhere else. This is not a periodic function, right? If it were a periodic function, then it would alternate between plus and minus, plus and minus, plus and minus everywhere along the axis. But we don't have something that is alternating everywhere along the x-axis. we have something that's alternating in just a few places. And then everywhere before that and everywhere after that, it's 0. This is not a periodic function. Non-periodic functions cannot be represented by Fourier series. Non-periodic functions are represented by Fourier transforms. So this would have to be represented by a Fourier transform. Is that what you were asking about, Diego? Or did you have other questions on that? Now, Stephen, I can't tell from your comment in the chat. You say you're confused on the piecewise function part. Are you talking about the piecewise function part of 1b? Or are you talking about problem 3, which involves the top hat function being defined piecewise? The question I was going over previously was the convolution. Okay, you get it now. What else? What else do people want me to go over? Midterm 2, question 2. Sure, midterm 2, question 2, that's perturbation theory. We went over this one with the previous group. So we need to find the eigenvalues of this matrix, and then we need to expand them for small epsilon. So the way we find the eigenvalues is we subtract lambda times the identity matrix. And now we're trying to find the determinant of this thing here and set that determinant equal to 0. Well, here's the determinant. You can write it out like that. We get a quadratic equation. We solve it, and then we have to expand it, which means we've got a square root of something that we're assuming to be small. Expanding, it says explicitly in the problem that epsilon is much less than e. So 4 epsilon squared is the tiny part. E squared is the big part. I can factor out the e squared. And since it's under a square root sign, the square root of e squared becomes e. And I'm left with 1 plus 4 epsilon squared over big E squared. Okay? And then I take the Taylor series of that. And you could either do the derivatives by hand, or you could just remember that handful of really important Taylor series: logarithm, exponential, sine, cosine, and 1 plus x to the n. Well, here we've got 1 plus x to the n. X is 4 epsilon squared over e squared. That's x, the tiny thing. N, the power, is 1/2. So I get 1 plus 1/2 4 epsilon squared over e squared. And 1/2 of 4 is 2. So I get 1 plus 2 epsilon squared over e squared. Any other questions about that one before we move on to another problem? All right, what else do people want me to go over? Problem set 13, question 4. All right, well, that one was big and messy. First of all, let me assure you that I'm not going to ask you to go through that many rounds of derivative gymnastics on the final exam. But we did go over this one with the previous group. And the most important thing there, let me see if I can find it. I know I went over it with them somewhere. Okay, I'm not finding it now, so I'll just start it from scratch. It's no big deal. Here's the thing. Psi is equal to y1, 1, theta, phi times some function of r times, I think it was sine omega t. Is that right? How was it written? It was 1 minus 1, but that's not going to matter. You'll see why. Times e to the minus I omega t. Okay. The question is, if it's, is it a solution to the wave equation? Well, the wave equation is partial squared psi, partial r squared, plus 2 over r, partial psi, partial r, plus 1 over r squared times angular derivatives. And I could write them out explicitly in terms of sine theta and derivative with respect to phi and everything. All of that should be equal to 1 over c squared, partial squared psi, partial t squared. Well, one thing we know about the spherical harmonics is that when we take all those angular derivatives of YLM, the whole point of writing out the angular derivatives of YLM is that you get minus L times L plus 1 times YLM. So what we can replace all of this with is partial squared psi, partial r squared, plus 2 over r, partial psi, partial r, plus 1 over r squared times negative 1 times 1 plus 1, because L equals 1, so L plus 1 equals 2. And then the second derivative with respect to time gives us a minus omega squared. So we get minus omega squared over c squared psi. That's what we have. And then it just becomes a question of, all right, we've done the angular derivatives. And the whole point of using spherical harmonics is so that you don't have to take derivatives of these complicated combinations of sine and cosine of theta and phi. You just know that the angular derivatives of the spherical harmonics are minus L times L plus 1 times the original function. And then we do the derivative gymnastics of the part that depends on R. So that's what I wanted you to do in there. I wanted you to just do the derivatives with respect to R and use the fact that these are the angular derivatives. Some people made this way too easy. They just said, oh, the angular derivatives are L times L plus 1. So yeah, this is a spherical harmonic. Spherical harmonics show up in wave equation solutions. Boom, we're done. Well, no, you're not done. Because to show that it satisfies the full wave equation, you need to take all of the derivatives, not just the angular derivatives. Other people made it way, way, way too hard. They took all the derivatives with respect to R, which are unavoidably necessary. And then they took the derivatives with respect to theta and phi in the hardest way possible. What I was hoping you would do is sort of the Goldilocks and the Three Bears solution. Don't do the method that's way too hard. Don't do the method that's overly simplistic. Do the one that's just right in the middle. The function of the spherical harmonic, its angular derivatives are known. You still have to do the derivatives with respect to R. So you're doing half of the derivatives in this problem. And those do get messy, but it's easier than doing the angular derivatives by hand and harder than just doing the angular derivatives and nothing else. So it's just right. It's the Goldilocks and the three bears solution. Think about it that way. Other questions? People aren't sure, then rather than just sitting here kind of awkwardly, I'm not going to send you all away, but I'm not going to have you sit here awkwardly either. Let's take a 5-minute break. Think about what questions you want me to go over. I'm going to check email and do a few other quick little tasks in the next 5 minutes. And then we'll reconvene 5 minutes from now. And you tell me which other questions you want to go over now that you've had a chance to look at it. All right, what else can I go over? All right. Problem set 14, follow-up, last question. So we were given two different versions of the wave equation. In one of them, we've got d by dx of, 1 over n squared of x d psi dx. And the other, we've got 1 over n squared I'm writing the second derivative that way. I'm going to put a 1 in there. Now, in both of these formulas, we've got an eigenvalue here. Our eigenvalue is minus omega squared over c squared. In one of them, p of x is 1 over n squared. But in the other one, it would be better to multiply both sides by 1 over n squared, put the n squared of x over here, and this would be rho of x. You could say, hey, there's no rho of x in the first one. Sure there is. It's 1. Multiplication by 1 is just normally not written out explicitly, but it's there. So in this first problem, or in this first half of the problem, the orthogonality relationship is that the integral of psi I of x, psi j of x dx equals 0 if I is not equal to j. And this would presumably be from minus infinity to infinity, but I'm not going to be too nitpicky about that since I didn't state much about it in the problem. Or did I? I don't think I stated much about that. Let me double check. Yeah, I didn't state too much about that. In the second one, rho of x is n squared. So in the second problem, minus infinity, the integral of n squared of x, psi I of x, and really there should be a star there, not that it matters much. If I is not equal to j. So depending on how we frame the wave equation, we get two different orthogonality relationships. And you will see the wave equation written both ways. You might think, well, which one is it? Which one does the physical universe obey? And the answer is that it depends on the boundary conditions that the wave satisfies. Both of these are simplifications of the full three-dimensional wave equation, which is in turn a simplification of Maxwell's equations. Depending on the types of solutions to Maxwell's equations that we're looking at, transverse electric or transverse magnetic, which comes down to boundary conditions at interfaces between two different kinds of materials, you could get the wave equation written in either form. And so it's just a matter of what physical situation are we looking at. You'll see both equations. Before I move on to the next ones that were referenced in the chat, are there any questions about what I said there? Okay, problem set 13, number 2.
Dr. Small?
Yeah.
So when you were talking about the form of which the wave equation occurs, depends on the boundary conditions which it satisfies.
Uh-huh.
Can we see that in the orthogonality relationship that you have on the right?
The orthogonality relationship that I wrote down does not make the boundary conditions at all obvious.
Okay.
The differential equation makes the boundary conditions somewhat more obvious because in the differential equation, if I've just got a second derivative, well, you can only take derivatives of continuous functions. So if I've got a second derivative, then obviously the second derivative is a derivative of first derivative. Well, that first derivative wouldn't be defined unless psi were continuous. And the derivative of the first derivative wouldn't be defined unless the first derivative was continuous. Now in the other equation, we don't have the second derivative on its own. We have the derivative of 1 over n squared times the first derivative. So again, in order for that first derivative to even make sense in there, psi has to be continuous. Likewise, in order to take the derivative of 1 over n squared d psi dx, 1 over n squared times the first derivative has to be continuous. If 1 over n squared times the first derivative is not continuous, then we can't really take a derivative of it. Now, technically, there are some things we can do with delta functions. Let's not go there today. For normal purposes, even those things that we do with delta, we're just not going to go there today is the bottom line. So we'd have to have a delta function on the right-hand side in order for any of this to make sense. But if we don't have a delta function on the right-hand side, which we probably don't, then we have to have 1 over n squared times the first derivative being continuous. Which interestingly means that the first derivative itself doesn't have to be continuous. The first derivative could be changing abruptly. 1 over n squared could change abruptly. But when we multiply this changing 1 over n squared by this changing first derivative, we get something that's nice and continuous. That actually happens when you solve problems with EM waves.
Got it.
All right, identities for spherical harmonics. You were supposed to find on this one that the sum over m of YLM squared is independent of theta or phi. Or more specifically, that the sum of the absolute value squared of YLM would be independent of theta or phi. Now, for L equals 0, it's trivial. YLM is just Y00, 0, which is square root of 1 over 4 pi. Squaring that is clearly independent of theta and phi. For L equals 1, let's see, for L equals 1, we get a sine squared theta plus a cosine squared theta plus another sine squared, but they have different coefficients. And so when you put all of them together, you get sine squared plus cosine squared. Basically, you get 3 over 8 pi sine squared plus 3 over 4 pi cosine squared plus another 3 over 8 pi sine squared. And 2 times 3 over 8 pi is 3 over 4 pi. So you get 3 over 4 pi sine squared plus 3 over 4 pi cosine squared. But I'm guessing that's not what the question is about. I'm guessing that the question is about L equals 2, which is very messy. You've got 5 terms. Some of those terms have cosine squared or sine squared theta. And so when you square them, you get cosine to the 4th and sine to the 4th. If the question is, can I walk you through the algebraic gymnastics right now? My very strong suggestion is that you study the solutions. The question is, will I require that level of algebraic gymnastics on the final? Probably not. At most, I would have one question that required some algebraic gymnastics. So if you got everything else, you'd be fine. I would give some partial credit, but I'm not looking to have a bunch of algebraic gymnastics on the final. I'm much more interested in, do you know which functions to use in the first place? So does that answer Jason's question? Jason, do you want me to say more about that? And feel free to use your microphone.
I think I got it.
All right, now Stephen, you said question two. Question two on what? Anything else? Problem set 12, parts A and C of problem 5. All right, let me pull that up. Okay, so the question there, part A, you were supposed to construct a series and tell me how AN plus 2 depends on AN. So I can walk you through the algebraic steps, but the main thing to note is that when you take that second derivative, you are going to get n times n minus 1, which means that a few things are 0. But then you multiply by z squared. So you wind up getting two very different things, and you can reset some terms via the tricks that we wrote out a few times in the book and on one of the practice assignments. Do you want, we could walk through that if necessary. But then let's see what you had to do in question 3. For what values of lambda will this series reduce to a polynomial with a finite number of terms? If you did it correctly in part A, so let's see, this is problem set 12, 5A, you're going to get that AN plus 2 is minus AN times lambda minus n squared minus 2n over n plus 1 times n plus 2. All right. N is an integer. And if you do this, if lambda happens to equal, say, j squared plus 2j, so some integer squared plus 2 times that integer, then when n equals j, an plus 2 is 0. That's the whole idea of part C. First, you get that messy formula in part A. Then once you've got that, if lambda happens to be a very carefully chosen integer, then it will eventually terminate. You will eventually have just a polynomial with a finite number of terms. So this is true if j equals 0, lambda equals 0. If j equals 1, lambda equals 1 squared plus 2 times 1, or 3. If j equals 2, lambda equals 2 squared plus 2 times 2 equals 8, and so forth. So these were three possible values of lambda, 0, 3, and 8. And they would go up to powers x to the 0, or a constant, x to the 1, something linear, or x squared, something quadratic. Now the linear ones are simple. The linear and constant are simple. If we just say that a0 equals 0, then a0 plus 2, sorry, a0 equals 1, my bad. a0 plus 2 is going to be minus a0 times 0 minus 0 over 0 plus 1, 0 plus 2. Now we have to assume that all the odd ones for that are 0. Lambda equals, so basically I should be saying a0 equals 1, a1 equals 0. For lambda equals 1, now we're trying an odd polynomial. a0 is 0, a1 is 1. Well, as soon as a0 equals 0, then the same can be said of a2, 4, 6, 8, and whatnot. a3, oh, sorry, lambda should be equal to 3, my bad. a3 would be minus a1 times 3 minus 1 squared plus 2 times 1. So 3 minus 3 is 0 over now the difficult part is if lambda equals 8. All right, then we say a0 equals 1, a1 equals 0. So we're doing an even polynomial. a2 is going to be minus this should be a0 times 8 minus 0. Technically I should write this 0 squared minus 2 times 0 over 0 plus 1, 0 plus 2. So I'm going to get minus a0 times 8 over 2, or minus 4a0. Then we check and see, okay, what's a4? Well, a4 is going to be minus a2 times 8 minus 2 squared minus 2 times 2 over 2 plus 1, 2 plus 2. It's 8 minus 4 minus another 4 is 0. So the polynomial terminates there. What else would you like to know, Stephen? Okay, what else can I go over? Problem set 14, number 5. The vibrating drum. So that one I went over previously, so let me scroll to those notes if I can find them. So a solution to the wave equation is going to be a Bessel function of order m times, or Bessel function of some order multiplied by e to the I m phi times e to the minus I omega t. Well, here somebody just took the imaginary part of e to the minus I omega t. So that's also going to be a valid because they got a sign. So they just took the imaginary part. That's fine. That's going to give us a valid solution. Looks like they took a combination of solutions that have m equals +2 and m equals -2. But the Bessel function, whether m is +2 or -2, you multiply that e to the im phi by a Bessel function of order absolute value of m. So e to the im phi and e to the -im phi both get multiplied by J2. Now, in these problems involving vibrating membranes, we're assuming that the Bessel function is 0 at the edge. It's a fixed boundary. So J2 of KR must be 0. Well, there's a few ways that J2 of KR could be 0. It could be equal to 0 if KR is equal to the first 0 of the Bessel function. It could be 0 or first 0 of J2 to be specific about which Bessel function. J2 of KR could be 0 if KR is the second 0 of J2, or KR is the third 0, and so forth. So K is going to be a Bessel function 0 divided by R. And then omega is equal to the speed of the wave multiplied by K. So omega is going to be C times the Bessel function 0 over R. Does that clear it up? Okay, what else?
May we go over problem set, let's see, what is it? 12, number 3, the question about a driven oscillator.
Okay, so we were looking for a particular solution. And I said, no, not the full solution to the homogeneous equation, because for that we would need some initial conditions. But at long times, it turns out that the homogeneous solutions go to 0, because the homogeneous solutions have an exponential decay in them for this problem. So we just want, let me write this down. So problem set 12, number 3. What you basically do whenever you've got an inhomogeneous problem is you guess that the particular solution is going to be similar to the thing on the right, and it usually is. So if we just guess that X is some amplitude e to the I omega d, where d means driving force T, well then d squared X by dt squared, sorry, m d squared X by dt squared plus beta dx dt plus kx must be f naught e to the I driving frequency t. And the derivatives, each time you take a derivative, you're just going to get a factor of I omega. So we're going to get minus m omega squared plus I omega beta plus k all times a e to the I omega dt equals f naught e to the I omega dt. So A is just F naught over K minus M omega squared D plus I omega D beta. Is that cleared up?
Yep.
What else can I go over?
All right, I gotta go. Thank you, Dr. Small.
You're welcome, Sebastian. Well, I'm not hearing anything else. Wait, is there something in the chat? Okay, we already had a break and you had a chance to come up with a list of questions during break. People have been asking questions for a while since the break, and now I'm not hearing anymore. So unless somebody comes up with something in the next 10 seconds, I'm just going to call this over. You can always email me over the weekend, but otherwise we can call it quits soon. All right, everyone. Let's call it a day. Good luck studying this weekend. I'll be available by email. And like I said before, on Monday, I can't promise to be in front of Zoom every single second, but if you email me, I'll make sure that I clarify any ambiguities on the final relatively quickly.
Thank you, Dr. Small.
All right, take care, everyone.
Thanks, Dr. Small.
You're welcome. Bye.